Although thorium, with atomic number 90, has 6 naturally occurring isotopes, none of these isotopes are stable. However, one isotope, 232Th, is relatively stable, with a half-life of 14.05 billion years, considerably longer than the age of the Earth, and even slightly longer than the generally accepted age of the universe. The isotope makes up nearly all natural thorium. As such, thorium is considered to be mononuclidic. It has a characteristic terrestrial isotopic composition, and thus an atomic mass can be given. Relative atomic mass 232.03806. 30 radioisotopes have been characterized, with the most stable being 230th with a half-life of 75,380 years, 229th with a half-life of 7,340 years, and 228th with a half-life of 1.92 years. All of the remaining radioactive isotopes have half-lives that are less than 30 days, and the majority of these have half-lives that are less than 10 minutes. One isotope, 229th, has a nuclear isomer with a remarkably low excitation energy, recently measured to be 7.6 plus or minus 0.5 electron volts. The known isotopes of thorium range in mass number from 209 to 238. Some notable isotopes: thorium-228. 228th is an isotope of thorium with 138 neutrons. It was once named radiothorium, due to its occurrence in the disintegration chain of thorium-232. It has a half-life of 1.9116 years. It undergoes alpha decay to 224 Rth. Occasionally it decays by the unusual route of cluster decay, emitting a nucleus of 20 O and producing stable 208 petabits. It is a daughter isotope of 232U. Th-228 has an atomic weight of 228.0287411 grams mole. Uranium-232 decays to this nuclide by alpha emission. Thorium-229. 229th is a radioactive isotope of thorium that decays by alpha emission with a half-life of 7,340 years. 229th is produced by the decay of uranium-233, and its principal use is for the production of the medical isotopes actinium-225 and bismuth-213. Thorium-229 meters gamma-ray spectroscopy has indicated that 229th has a nuclear isomer 229 mth with a remarkably low excitation energy. This would make it the lowest energy nuclear isomer known, and it might be possible to excite this nuclear state using lasers with wavelengths in the vacuum ultraviolet. The isomer might have application for high-density energy storage, an accurate clock, as a qubit for quantum computing, or to test the effect of the chemical environment on nuclear decay rates. The lifetime of the isomer has been measured to be 6 plus or minus 1 hours. The measurement was done by collecting recoiled 229 mth atoms in a MgFs crystal and measuring the light emission variation over time. If this isomer were to decay, it would produce a gamma ray in the ultraviolet range. The isomer transition energy of 229th is currently derived from indirect measurements of the gamma-ray spectrum resulting from the decay of 233U. In 1989 to 1993, first measurements were performed using high-quality germanium detectors, resulting in an estimate of E equals 3.5 plus or minus 1.0 electron volts for the 229th isomer transition energy. This unnaturally low value triggered a multitude of investigations, both theoretical and experimental, trying to determine the transition energy precisely and to specify other properties of the isomer state of 229th. However, searchers for direct photon emission from the low-lying excited state have failed to report an unambiguous signal. New indirect measurements with an advanced high-resolution X-ray microcalorimeter were carried out in 2007, yielding a new value for the transition energy of E equals 7.6 plus or minus 0.5 electron volts. Corrected to E equals 7.8 plus or minus 0.5 electron volts in 2009. This value is currently the most accepted one in the community but cannot be considered definite until a direct measurement is made successfully. The shift into the VUV domain probably explains why previous attempts to directly observe the transition were unsuccessful. Thorium-230 is a radioactive isotope of thorium that can be used to date corals and determine ocean current flux. Ionium was a name given early in the study of radioactive elements to the 230th isotope produced in the decay chain of 238U before it was realized that ionium and thorium are chemically identical. The symbol IO was used for this supposed element. Thorium-231 has 141 neutrons. It is the decay product of uranium-235. It is found in very small amounts on the Earth and has a half-life of 25.5 hours. When it decays, it emits a beta ray and forms protactinium-231. It has a decay energy of 0.39 MeV. It has a mass of 231.0363043 grams mole. Thorium-232 as thorium is mononuclidic. The main article on thorium effectively discusses this isotope. 232Th is the only primordial isotope of thorium and makes up effectively all of natural thorium, with other isotopes of thorium appearing only in trace amounts as relatively short-lived decay products of uranium and thorium. 232Th decays by alpha decay with a half-life of 1.405 times 1010 years, over 3 times the age of the Earth and more than the age of the universe. Its decay chain is the thorium series, eventually ending in lead 208. The remainder of the chain is quick. The longest half-lives in it are 5.75 years for radium-228 and 1.91 years for thorium-228, with all other half-lives totaling less than 5 days. 232Th is a fertile material able to absorb a neutron and undergo transmutation into the fissile nuclide uranium-233, which is the basis of the thorium fuel cycle. In the form of thorotrust, a thorium dioxide suspension, it was used as contrast medium in early X-ray diagnostics. Thorium-232 is now classified as carcinogenic. Thorium-233 is an isotope of thorium that decays into protactinium-233 through beta decay. It has a half-life of 21.83 minutes. Thorium-234 is an isotope of thorium whose nuclei contain 144 neutrons. Th-234 has a half-life of 24.1 days, and when it decays, it emits a beta particle, and in so doing, it transmutes into protactinium-234. Th-234 has a mass of 234.0436 atomic mass units, and it has a decay energy of about 270 keV. Uranium-238 usually decays into this isotope of thorium. Table. Bold for nuclides with half-lives longer than the age of the universe. Abbreviations. CD. Cluster decay EC. Electron capture IT. Isomeric transition SF. Spontaneous fission. Bold for stable isotopes. AB intermediate decay product of 235U. Intermediate decay product of 232Th. Used in uranium-thorium dating. AB intermediate decay product of 238U. Primordial radionuclide. Notes: geologically exceptional samples are known in which the isotopic composition lies outside the reported range. The uncertainty in the atomic mass may exceed the stated value for such specimens. Values marked # are not purely derived from experimental data, but at least partly from systematic trends. Spins with weak assignment arguments are enclosed in parentheses. Uncertainties are given in concise form in parentheses after the corresponding last digits. Uses: thorium has been suggested for use as a source of nuclear energy. Presumably, it would need to be exposed to neutrons in a nuclear reactor to convert the common isotope to some species that is fissionable. It is currently used in cathodes of vacuum tubes for a combination of physical stability at high temperature and a low work energy required to remove an electron from its surface. It has, for about a century, been used in mantles of gas and vapor lamps such as gaslights and camping lanterns. Its radioactivity is a consideration for its non-nuclear uses but is too small to rule it out. Thorium was also used in certain glass elements of aeroactor lenses made by Kodak during World War II. Thus they are mildly radioactive. Two of the glass elements in the f2.5 aeroactor lenses are 11 and 13% thorium by weight. The thorium-containing glasses were used because they have a high refractive index with a low dispersion, a highly desirable property. Many surviving aeroactor lenses have a tea-colored tint, possibly due to radiation damage to the glass. As these lenses were used for aerial reconnaissance, the radiation level is not high enough to fog film over a short period. This would indicate the radiation level is reasonably safe. However, when not in use, it would be prudent to store these lenses as far as possible from normally inhabited areas, allowing the inverse square relationship to attenuate the radiation.